Hello, everybody, to my talk. My name is Olivier Giroux. I work for NVIDIA. I've been at NVIDIA for 15 years now. I've worked on 8 different GPU architectures, and more recently, 4 different SM architectures within these GPU architectures. And SM, in this case, is a compute core. So I guess that makes me old enough that there are some people here who've never used GPUs that I haven't worked on. Now, I'm here to tell you something really exciting, and that thing is that NVIDIA actually really cares about C++, so much so that I can come out and say quite clearly that we designed this one, which is Volta, the one we announced this year, specifically with C++ in mind. And so my talk, designing C++ hardware, in my view of it, it is both designing new hardware for C++ and designing new C++ for hardware, and doing all that at the same time. So to put me into some coordinates in space here for you, I've said I work at NVIDIA. I'm a GPU architect. I'm also a member of WG21, which the contrast here is not really great, but I'm also a member of WG21. I've been on the community for several years now. And I'm a member of an even smaller community that deals in memory models, these obtuse axiomatic definitions of what it means for memory to be memory. OK, so that's my perspective. And the agenda today is largely not code. And in fact, there will be, this is an accurate depiction of what we're going to talk about from a high level. When we do talk about code, it will actually be fairly bad code. I apologize in advance. OK, so now I have a question to start with. And that question is, what is it about C++ that makes it portable? We like to think that C and C++ are languages that are portable to a wide variety of computer systems. But when you look out today, is there that much variety? That's an evidence of that. OK, so what is it about C++ that makes it portable? And I think that if we ask this question at the water cooler in most of your organizations, we might get a list that looks a bit like that. Like there are things like you don't really get to know how big char is. You don't really get to know how big anything is. Your integers, they might be 2's complement, but they might not. Your floats, they might be IEEE or they might not. You don't really know about the endianness of addressing. You don't get to control the alignment of certain things. Especially, you cannot undercut the minimum alignment of a type that the platform chose. And then there's this thing called segmented memory that C++ supports through various arcane rules. OK, so in this view, C++ has robust support for all of these weird things across the storage abstractions of the language, across the arithmetic abstractions of the language, largely through various forms of undefined behavior on the arithmetic of integers, for example. Not that they are not 2's complement. OK, now I have some. This may not. It may come as a shock. May not come as a shock. But largely, most of this also has you covered for the 20th century Trivial Pursuit, meaning there are essentially no remaining well-alive systems that care about any of this. Except for the bottom 2, which may surprise some of you. So we've got this stuff in C++. Because C++ has robust support for these things, which are really, is support for fossils. Not living systems. OK, so how useful is that? In my experience of trying to create a new implementation of C++, I haven't found these things to be very useful. And by the way, the odds of making a genuinely new computer architecture that supports C++ are really stacked against you. The odds are you're just going to gravitate to copying one of the pre-existing ones. OK, so why is most of this not helpful? Well, it's because behind these things are either a lot of false choices or bad choices. If you're going to create a new architecture today, let's say you're getting funding to create a new processor tape-out, Well, most of these options are really going to be dictated to you. If you're making a new CPU, pretty much everybody's going to go match what ARch64 is doing. Because ARch64 went ahead and updated the Linux kernel with all the support they needed. Are you going to do the same? No, probably not. You're going to want to stream behind them. Okay, so for a new CPU, you'd probably look to match ARch64. If you're making a GPU, you have to match the host. If the host is using a 32-bit 2's complement int, you also need to be using a 32-bit 2's complement int. Because otherwise, the GPU won't be interoperable with the CPU. In fact, for GPUs, what that means is that we end up matching all the hosts. It used to be that NVIDIA GPUs had a switch in them to switch them from little endian to big endian, because we wanted to be attached to big endian systems. Okay, and that went away. The big endian systems went away, and so did the switch. And then other choices are just bad at this point. Sure, you could build a 1's complement machine. Sure, you could build a non-IEEE float machine. But at this point in 2017, you would get really negligible area savings or power savings from that. But you would pay on the software side. Your users would suffer from all the rediscovering all these nits, which we know in the C++ community, and it makes us really cool at the water cooler when we talk about that. But most programmers don't really worry about it on a day-to-day basis. Okay, so now I'm going to make sort of a weird comparison. I'm going to compare the manufacturing processes that NVIDIA tape-outs used at the time of various C++ revisions. And I think this weird comparison makes sense in my head because, in my view, C++ implementations go all the way down to the metal. By metal, I mean a periodic table metal. Okay. They don't stop at a particular arbitrary point in the middle called an ISA. The C++ implementation is not just the job of taking a program and lowering it to an ISA. It's taking a program and making a complete physical manifestation of that program, all the way down. Okay, so if you were to tape out C++ in those years, what manufacturing process would you use? And these are to scale. Okay, so in 1998, NVIDIA was using 350 nanometer lithography. In C++ 17, we're using 12 nanometer lithography. A bunch of design, you would think such a dramatic change in the landscape would affect certain design decisions. There are design decisions you make differently when you have, by now, giant transistors or tiny transistors. Okay, so at some point in there, IEEE floating point became a no-brainer. As far as we are concerned, we would not bother taping out for our main math units, for our primary math units, we would not bother taping out non-IEEE floating point. It just doesn't really make sense. The units are small at around this time, like around between 130 and 40. It's just a non-issue. Okay, so we're not interested in that freedom starting on that point. And my argument here is most of the other things that are on the previous table, they all fall to a similar argument at some point on the timeline. They're no longer a freedom you're interested in exercising. Okay, so I would say that there are sort of these epochs of C++ design. And by here, I'm really talking about the language design. In the early days, in this revisionist history that I'm doing here, in the early days, priority is to make sure that you can make little systems legal. Systems that have decided to throw overboard some complexity because you're coming from a mini computer to a microcomputer, and you couldn't afford to have all these units and have all of them behave the same way. And so the language enables lower QoI options, lower quality of implementation options. But in the future, we have a different problem. Our problem is making sure that C++ legalizes really big systems. Okay, so for the rest of the talk, we're going to talk about sort of non-classic portability. And these are these two phases that I just talked about. Then an era of transistor scarcity, and now a completely different era of transistor abundance. In 7 nanometer, you can put so many. Question is, can C++ actually use them? If I fill a really big die with functionality, how will C++ get to it? Okay. And I would say, also slightly revisionist history, I would say that in C++ 17 we have taken steps in that direction. Okay. So what is it about the next C++ that makes it more portable? I would like to talk to you about topology. Here's a really simplistic diagram of a computer. I mean, you see these diagrams in textbooks. I have a line, and I'm going to call it a bus, and then I hook a CPU rectangle and a DRAM rectangle onto this. And I'm going to call this a 1980s type of topology. Okay, so there's my 1980s computer. Oh, and there's other things in my computer, of course. My computer's got lots of other features. All of them are I/O. Okay, so there's the CPU, and there's the RAM, and then everything else in the world is I/O. And really the interface here was probably invented to serve as tape drives, but it's okay, we'll work with it. All right, so then C++ comes in, and obviously in C++ I am not programming a CPU and DRAM directly, I'm using abstractions. So C++ introduces layers of abstractions. In fact, C++ alone brings in at least 3 layers of abstraction for each side. We abstract the CPU using threads. We virtualize it using threads. We have this abstract notion of an execution agent that a thread is a concrete example of. And then I have the thread of execution, which is a chain of value computations in your program. One independent chain of value computation in your program is the thread of execution. At that point, that's pretty much your code. Okay, so those are layers of abstraction there. And then on the DRAM side, I have a similar thing. I have allocations, which have objects, and then the objects hold values. Okay. Now, from that time to more or less today, here's what we've achieved. We've been able to dice the box on the left into parts. We have achieved that. Now, they still pretty much have to behave as one. They have to be friends. They have to be friends when they access the memory. They need, in order to make sure that that they're all coherent, for example. Okay. Now here's the problem that I have. My design expands the topology of the system in a way that was not originally envisioned. It was not originally envisioned in C++. There are no abstractions to deal with another coprocessor. The coprocessors went away when the 386 integrated the FPU, right? So there are no coprocessors. The notion of whether they're equal or not doesn't compute because there are none. So there are no abstractions for that. But even at the fundamental level, even in my computer architecture diagram, it also doesn't work. Like, how is my coprocessor equivalent to I/O? And this is actually a real weird thing today. Operating systems program my GPUs using I/O controls, IOCTLs. It is basically receiving these commands as if it were a disk drive. Okay. But it's not. It has a very large number of cores in it, effectively. It has a very large number of parts. Now, I put 2 numbers there. It sort of depends how you interpret it. It can execute 5120 different instructions per clock, every clock. They're not all different, but they're going to be, like, some of them are going to be similar. Yeah. But it has an abstraction on top of that, also of threads, of which there's 163,840. So I don't know how many of you have written concurrent programs with 163,840 threads in them, but that's basically been my summer. All summer, yeah. Okay, so the future scalability of C++ goes through showing some love for topology, caring about more interesting topologies that make bigger and bigger systems. So this diagram here is not even particularly crazy. This is a system that we're shipping. There are some of you in the room who probably have one now. So this is one of the systems that we're shipping that has 8 GPUs and 2 CPUs and a bunch of network connections, and then there's all kinds of connectivity in there. We can imagine way crazier. Okay. All right. So far we've talked about things in C++ that make it more portable and sort of future directions that we should care about. Now this talk is called Designing C++ Hardware. So now we're going to switch to how did we design. I made the statement up front that Volta, our GPU architecture from this year, that Volta was designed for C++. So let's dive into that claim. I'm breaking it up into 2 parts. We're going to talk about how we're attacking the memory vertical, right? There were 2 verticals on my previous slide. You know, how are we attacking the memory vertical, and how are we attacking the execution vertical? Yeah, we're going to talk about those 2. So let's start with the memory vertical. At the diagram level, at the theory level, you know, as long as I have a diagram with 2 boxes and 3 lines, you know, it appears so simple. There's a bus, and there's a processor, and it's attached to the bus, and the memory is also attached to the bus, and the processor goes and accesses the memory. Should just work. Okay. But the reality is a lot more like this. You know, the memory is really attached to the CPU, right? It's not really on this bus. And the CPU has a very special access to the memory. And it really, and this is really, you can quote me on that, it's really my terminology, I use it regularly. It tastes like memory. When the CPU goes to memory, it tastes like memory. It has these attributes that you expect. For example, a series of loads and stores to the same address from the same thread never become reordered. That sounds like pretty key. Like if I were polling on a memory location and I saw that memory location become 1, I would expect that I don't need to test it again after the polling, that it wouldn't just become 0 again. Like, unless someone else wrote 0, of course. But, now, that's really not the life experience of someone working on the other side of this line. I said that everything below this line is treated as I/O. And so, as we go to memory, it's really like we're traversing this complicated maze, which might be a series of different buses with exchanges and switches, and it's really not that simple. And somewhere along the way, one of these switches just really likes to reorder things. And so when I go to memory, it doesn't taste like memory. It tastes like DMA. Okay. We've done a lot of work on this. Actually, you know, all of this talk is notionally about Volta. The next slide is mostly not about Volta. The next slide is about the work we've done over a decade-long period of making memory in CUDA C++ live up to the expectations of C++ programmers more and more. Okay, so if you think of GPU programming as being, I use this GPU alloc and then I do GPU memcopy, and I have to do GPU memcopy in and I have to do GPU memcopy out, you're really thinking of CUDA 1.0, which at this point is 10 years behind me. Okay. Those were the first generations of GPUs that had compute capability. I said that I worked on 8 GPU architectures. So before that, I worked on Rankin and Curie, which did not have any compute capability. They were graphics-only devices. Okay. So here we are. That's the first generation, and you know, CUDA made a very big splash, and it was imitated far and wide. And so this model of CUDA 1.0, you can now find it on a variety of platforms from a variety of vendors. They're all more or less copies of that. Okay, but we didn't stop there. In Kepler and Maxwell, we created this different API called CUDA malloc manage. And CUDA malloc manage uses this symmetric heap approach, where basically allocations that you make on the CPU with that become mirrored on the GPU when you launch some work, and they are mirrored at the same address. So as long as you don't have any data races between your CPU and GPU threads, and so we disallow your own custom synchronization between CPU and GPU, and you have to use our heavyweight synchronization, as long as you follow our rules, then actually already at this point, memory pretty much feels like memory. But there is one big downside, which is that we are making a symmetric copy of the heap at every invocation, from the CPU to the GPU and back. Okay. So we didn't stop there. In Pascal is really when we introduced another mode of CUDA-malloc manage, where it can migrate the data on demand. It's basically, it's notionally similar to a copy on write scheme. Okay? And we've basically continued that. We've continued that in Volta. And this, I cannot wait for this to land. There is a patch in the queue of the Linux kernel maintainers that adds, effectively, that merges this into the operating system as an extra level of paging. And then when you have that patch in your kernel build, basically now everything goes away. It's just malloc. It's just any malloc. Actually, even memory that's not malloc. Could be memory on your stack. Could be a global variable as static. Those would all be fine. It's basically, at that point, the memory that's backing the whole application, not only is it pageable to disk, but it's also pageable to the device. Okay.
So if you had memory mapped file, for example, on the CPU side, you could normally read that from the GPU?
Yeah, yeah. The question was, if there was an M-mapped file, could the GPU use it? Yes. Yeah. Yeah. Okay. Yeah. At that point, when you have a Pascal and Volta or better, and you have the Linux HMM patch is either you have a custom build or it gets adopted and you have a kernel from after that date. At that point, the whole discussion of where the memory is, it just goes away. Okay. You'll notice that my table is weirdly shaped, and it's because there's another part to it. Okay. Now, we're not satisfied with this, this maze separating us from the memory. So you may have heard that we also have this thing called NVLink. And NVLink is a hardware capability that we've built, and we've developed it together with IBM, and IBM has implemented it in Power 8 and Power 9. And once we have an NVLink connection instead of a PCI connection, suddenly all of memory tastes like memory again. It does not taste like I/O. Okay, and so there's this other part here, which is that if we are talking about an ARM system, in which case it would be an NVIDIA ARM SoC, or a power system, Power 8 or Power 9, then there's also this other option down here. And under this option down here, there might not even be any paging. The memory is, at that point, fully unified in hardware. Okay. All right, moving on. So we've talked about coherency. Well, coherency is not enough. You also need consistency. And you'll recognize, effectively, this table is just a reproduction of your average implementation of C++11. There's some of the combinations of load stores and atomics are not valid. Some of the combinations are valid, and then there's consume, which everybody decays to acquire until such time as we as G1 fix consume. So there's your consistency for CPUs. So what should it be? What should it be for GPUs? Well, the answer is exactly the same. Absolutely exactly the same. And that is a new thing in Volta. Although the coherency became a feature on Pascal, the consistency model appears here with Volta. Okay. We have unfortunately the slide doesn't really do it justice. It's a completely new memory model. It, at 10,000 foot, sure, resembles some other models. For example, it somewhat resembles Power. It resembles other models that have scopes that have appeared for GPUs. But it is fundamentally different from the other scoped models in that it does not have undefined behavior for data races at the level of the instruction set. So it is in the vein of CPUs, where programs that have data races have loosely bounded behavior, but not undefined. And then it's at the language level that you have undefined behavior. Like in C++, it's undefined behavior. data races are undefined behavior in C++. But how bad can the machine get once you have data races is still something that you want to care about. Like the fact that your C++ program is undefined, if you have a data race, it's bad, okay. How much of that can be turned into an exploit somewhat depends on what the hardware will do. And so it's very important to us that we adopt sort of the best known art for defining a CPU, processor memory models, which had not been done before for a scope model. There are a few concepts that didn't exist in the literature that we had to create. And so now, I'm very lucky because this actually landed on the website, I think, 2 days ago. I can now hand you a URL to our formal axiomatic memory model. That was in development for a very long time. And so that gives me an opportunity to tell everybody that, oh my God, I really love the C++11 memory model. It's really fantastic. Whereas earlier, I listed some things that people might think help the portability of C++, but don't really. Here's an example of a thing you might not think of very much, but really, really helps the portability of C++. You all know that volatile is a bad word. But it is, although it's bad for software developers to use volatile, it is particularly oppressive for hardware architects when you use volatile. Because a program that has volatile in it does not actually have well-defined semantics. It only has the semantics that the machine you ran it on gave it, right? And so if most people do their development on x86, then it means that for most people, the semantics of volatile is whatever x86 did with that. And that would force us, and this is true story, we would end up in conversations endlessly where people are like, well, x86 did this. You should do this. And we're like, no, we can't. Like, we don't have the privileged access to the walled garden that owns the memory. So it's not even an option. It's not even an option for me to really go and match it. What the C++11 memory model did is it really clarified the semantics. Not only did it clarify the semantics, it clarified them in a way that made it completely implementable to me. So, so that was wonderful. That was very wonderful. Yeah. And as it happens, I joined the committee right after that, and then at that point, I thought, whew, we dodged a bullet there. We were not really paying attention, but we dodged a bullet. All right, a few open issues. I'm not watching time too closely. Okay, thank you. Okay, there are open issues remaining for C++ memory. Coherency and consistency, unfortunately, was not all of it. There is more. So now I'd like you to consider the issue of footprint, or working set, or could be a synonym for it. So here I have some example numbers for that CPU box and these DRAM boxes and the Volta box. All right, so I may have a CPU with 16 threads and 128 gigs of RAM. That is a perfectly reasonable system for somebody to assemble. And I have, in my PC, a Volta with 163,840 threads, and it has 16 gigs of RAM. Let's take a second here and look at these ratios. These ratios are not very similar. 1 to 8 gig and 1 to 100K, these are not very similar. So if you'll recall a few minutes ago, we were looking at the transistors and I said, you might imagine that with such a drastic difference in the amount of transistors you can have, it might change some design decisions. I would bring up to you that this would probably change your design decisions for libraries and even language design. Okay, so here's a concern that I have. And this is really an evolution of C++ thing. It's a thing SG1 has talked about. I'm going to give you a number for a paper. You can go read it and opine about it. I would like that paper to get a future revision, for instance. Okay. Shall we spend all of that on thread local? that is a really significant risk. People might use thread underbar local from C++11 with relative abandon when it's 1 to 8 gigabytes. But when it's 1 to 100 kilobytes, that's just not going to work very well. Okay. I would surmise that whoever came up with TLS didn't really think about systems with 163,000 threads. It probably did not occur to them. Okay. So we have a problem. We have something's got to give. We need some way to clarify that thread local may sometimes have a different meaning or something. I'm not sure. That's a wide open field. We could write something new. Okay. There's another issue. 163,840 stacks is a lot of stacks. In that 100 kilobytes, some of it goes to your stack, but hopefully not all of it. Okay. Concretely, in 2017, at NVIDIA right now, we are forced to choose between having stack accesses that have high performance or complying with Note 11 in clause 4.7 paragraph 1. What does that note say? It says, I'm paraphrasing, that automatics are private to a thread. However, you can take their address. And once you take their address, you can share them with another thread. And then other threads can access this object. Oh, and be aware of databases. Okay. As it happens, our current implementation is exceedingly efficient, but it does not allow addressing of this memory by any thread other than the thread that owns it. And I'm not sure how to reconcile these things, and it's not because I haven't thought about it. Okay, so memory progress report. Coherency, we're pretty much set from Pascal to Volta. Consistency, we're pretty much set on Volta. At the moment, it's at the assembly level. I don't mean the private assembly that you don't have. I mean the public assembly that you do have. And you can use inline assembly in CUDA C++. So you can have access to all the primitives that you need to get the same semantics that are compatible with C++. When atomic T appears in CUDA C++, that is currently TBD. But some people have prototypical implementations. Okay. That's on our side. That's on the GPU side. Oh, and I don't know what to do about footprint. Working set. This is effectively a problem that's just endemic to the scale. And my hunch is we're going to need to have a way for C++ to speak to that. Okay. The C++ disposition. There are some known bugs with the C++11 memory model. Nobody panic. It's fine. We're taking care of it. You could read P0668. A fun adventure. Some of the bugs there were co-discovered by Princeton and NVIDIA and a group in Germany at Max Planck. It's funny because they were all discovered at right about the same time. And then everybody was like, I have a thing to tell you. You'll never guess what it is. And we're like, wait, the proof of conformance of this processor is invalid? Like, yeah. Okay. So there are recommended fixes. We had a vote in Toronto to move ahead with the fixes. So we need to revise the paper and put it in, and then we'll have a relatively short defect list on the memory model after that. Okay, so that's the C++ disposition for coherency and consistency. I would invite people to look at P0072, half of which was adopted into C++17, and the other half was left on the shelf. I'm basically saying the half that was left on the shelf, we should think about it again. And if it's because it helps with the footprint problem. Okay. All right. Let's talk about designing Volta for C++ execution. And this year is, we did something really huge here. Okay, so huge, yeah. So I talked about these abstraction layers earlier. C++ has the concept of a thread of execution, which you have to use all three words and probably hyphenate them, because it's a term of art as a thread of execution, which is a chain of evaluations in your code. It's sort of your code representation of a thread. That runs on an execution agent, which is just an abstract notion for that thing which runs your code. And prior to C++17, there was only one instantiation of this concept. It was a concept with only one concretization, which is a thread. And that's just a particularly onerous version of that, really. I mean, the thread is in C++11 fairly fat. It has all these, the thread local and its behavior on the automatics, and it has a guarantee of forward progress. It's extremely strong and all that. Okay, so then what's lower down is CPU runs anything, that's for sure, and then the GPU it's a thing that doesn't run onerous things. Okay. All right. So in C++17, by adopting effectively that half of P0072, we've done a lot of clarification. We've clarified that actually execution agents might have more than one kind of instantiation. And there might be more than one kind of execution agent. So we've created the concept of concurrent execution agents, parallel execution agents, and weakly parallel execution agents, which basically differ among each other by the amount of forward progress guarantee that they have. A concurrent execution agent has all of the capabilities and all of the forward progress that a stud thread has. And also this special main thread that we can't tell you what its type is, but it's a main thread. And so that sets up sort of the old C++11 vertical, is right there. With the new types of execution agents, parallel execution agents do not have a guarantee for when they will start until you block on their completion. But once they've started running, they have a guarantee of forward progress. They can execute concurrent algorithms that are starvation-free, not just lock-free. And that is the most important distinction with the next class, weakly parallel execution agents, can only execute algorithms that are lock-free. That is, algorithms, concurrent algorithms that are correct even if threads are indefinitely victimized by the scheduler. Okay. Now, one of the things that you may already have noticed here is I've staked out this position that Volta is pretty unique because Volta is here, and then all other GPUs are here. Okay. This was not business as usual at all. This was a concerted effort by engineers who wanted to move the state of the art for vector thread execution. We literally threw out our entire implementation of GPU threads. We took all that RTL code, all that hardware code, that unit, tossed it out, and did something completely new. And when we designed it, we were basically making sure every step along the way that we were conforming with the C++ standard. We were quite literally quoting the C++ standard at each other while designing hardware. Okay. Okay, and that actually makes Volta very much alone of its kind. The tradition of making GPU-like threads is not all that new. It's almost as old as I am. But across that vast span of time, really nobody else managed to make a system that can execute starvation-free concurrent algorithms at vector efficiency. So that is completely new. Okay. And that allows us to clarify SIMT C++. SIMT is single instruction multiple thread. That's the name that NVIDIA has given to this type of architecture, and it's in comparison with SIMD. All right? All right. Now I'm going to show you that bad code. We're there. We're at that place where I have the bad code. So I'm going to show you some bad code that doesn't really have atomic T in it. So now we can clarify this. Here I have a piece of code which is largely, short of an annotation or two. It's basically CUDA 9. It's basically valid CUDA 9. Actually, as written here, it's valid CUDA for any revision of CUDA above 1.1 syntactically, but semantically only 9.0. And only on Volta. And the reason for this is, when you're running on a vectorized processor, whether it's SIMD with a compiler that inserted predication, or whether it's SIMT with either a previous implementation, which was stack-based, or this new implementation, which is, I'm not telling you. The problem is that the moral scheduler that runs these threads makes a choice after one of the threads exits the loop. Okay, so this is just a spin lock. I'm spinning on cast. Someone's going to succeed in switching the lock from unlock to lock, and then they're going to exit this loop. When they exit this loop, the machine has two paths. I can either execute the other threads in the loop, or I can execute the critical section. The problem is, any static compilation to predication, or our previous architecture, would commit to one of the two choices, and then it would have to run that path to completion. Which in this case here means you potentially could choose the while loop. The while loop is never going to succeed again, because the thread that owns the lock is attempting to execute the critical section, and it's being victimized indefinitely. So we never make it to the unlock. Okay. If you wrote this code in any revision of CUDA from 1.1 to even including 9.0, as long as you don't have a Volta, then you could lock your GPU with this. And you could, you could lock anybody's GPU with this. You could lock a compiler to predicated SIMD with this. Okay. All right. So what Volta just did is pretty huge. And although I can't share the details of how we did it, it's actually pretty wonderful in use. You write this code, it's just things you expect work in C++, and they just do, and without fanfare. It's like, you wrote it and compiled it, it ran, you're like, big deal. Well, big deal. This never worked on a processor with this kind of efficiency before. Okay. All right, there are still some open issues with execution as well. I talked about it. I had some open issues with memory. We have some open issues with execution, and this is where we're going to talk about the degree of conformance or not that we have. Okay. So basically, here's the short version of it. I don't want to give an extra 30-minute talk about all of the things that don't work, but basically, the state of heterogeneity hasn't really changed in quite a long time, and I'm not here to announce anything new with respect to that. That is basically, there's an annotation. In CUDA 9, it takes the form of the underbar host or underbar device annotation, where you say which device to compile the function to, or both. And this, in combination with the lack of integration between the compilers, the NVIDIA compiler and GCC, particularly, essentially do their jobs separately, and they're not very deeply integrated. This is basically what's behind what's remaining in conformance issues. So, RTTI doesn't work because we don't know the internal implementation of RTTI of every other compiler that we work with. So that's just an example. But more annoyingly for me, and probably for many of you in the room, is very simple things like std vector operator square bracket doesn't work, and it's because it's just not annotated with device. If it were, it would work because there's nothing complicated in here, but it's not, so therefore it doesn't work and it's rejected. But my personal experience writing CUDA all summer as someone who basically wrote essentially no CUDA before this summer. I pretty much waited for Volta to write CUDA. All I need to know is that I need to stick device on functions, and then everything will work. And practically everything else does work. Most language features you can think of just work. Okay, so here's the execution progress report. On the issue of forward progress, we have greatly clarified SIMT progress with Volta, and we simultaneously greatly clarified progress in C++ 17. That's not an accident. So that allowed us to clarify the meaning of SIMT C++. That's major progress. And then on heterogeneity, stay tuned. All right, so let me wrap up. Let me leave you with a wrap up on the Volta C++ architecture. Right. This is really the model that I want you guys to have in mind. We are sometimes, justly or unjustly, people are sometimes upset that we don't give full specs for our systems. Other companies give full specs for their systems. We reserve the right to be innovative in certain ways that are just not compatible with giving everybody our specs. But I want everybody to know this, that our platform is really a scalar platform. Like this, earlier I said compiling down to the metal, meaning element metal. For this slide, I'm going to say if you're compiling C++ to metal meaning instruction set, above this line, NVIDIA GPUs are scalar threaded machines. They are not SIMD machines. We do not present the SIMD abstraction at all. In fact, our instruction set, both the abstract instruction set that you have access to called PTX, and the concrete instruction set, which I work with on a daily basis, both of them are inherently scalar threads. We don't have FMA times 32 with a predicate. We have FMA of a scalar. And each thread executes its own copy of that FMA of a scalar. And it's the job of this layer that we have in the silicon that I'm labeling thread virtualization. It's the job of this layer to figure out how these operations can be ganged so that the power saving is realized without having any undue consequence on how you would build the software stack above. And I'm actually incredibly proud of this approach. I think that it supports really clean software stacks to map to our machine. Scalar compiler optimizations are old and well trusted and well verified and deliver the highest performance, really. We would not want to walk away from scalar optimizations because we prematurely committed to a vector execution. Okay, so to these layers of abstraction. Today, most of C++ 14 is supported by CUDA 9. There is, just like on the GCC and Clang web pages, there's a table of features and which papers they took the feature from. We have the exact same thing. So you can come on the NVIDIA developer website and see what the feature support matrix is for a compiler. And it is both the worst of any major compiler and by far the best of any GPU or throughput processor architecture. So it's somewhere in this middle. Okay. All right, so we have that, and that sits on top of an array of scalar threads, and the GPU is a scalar architecture. Okay. At this point, I actually have a really large number of backup slides that dive into various kinds of details about Volta specifically, but I'd like you to drive my going there with your questions. Yes, sir?
When you say that vector bracket doesn't work, I'm trying to...
So what do I mean when I say that vector bracket doesn't work? What you'll get is you'll get a compiler error. It'll say when you're writing, so when you write your code, some functions, you're gonna designate some of them as being GPU functions. When you write code inside of that function, you can legitimately pass in a reference to a std vector or a pointer to a std vector. That's fine. But then when you attempt to invoke the square bracket operator on this vector, you're gonna get a compile time error that says operator : std vector : operator bracket not device qualified. And that effectively means that the compiler is not going to generate a device version of the bytecode, the final executable bytecode for this function for the device, and therefore you can't invoke it. Now, there's this is an experiment that I did years ago. I opened up, I have no idea if that violates terms of service, but anyway, I opened up my Visual Studio headers and I just started typing down device like all over the place. And it worked just fine. Right. Now here there be dragons. Even if you were to do that, the standard library functions have no limits on like how much special stuff you can use internally. They can use x86 inline assembly for all they care. And then at that point, me sticking device on it is not going to help. So, okay. So that's what I mean. There's actually a fairly big pile of problems there. C++ assumes all the code is going to be generated to one architecture. The presence of another architecture in the abstract machine, at the moment, messes things up. It would take fairly significant compiler studies to figure out new ways of compiling the code to a way as well. Okay. Peter, and then you.
Yeah, I was just commenting. So what you're actually claiming is that the NVCC, is that the name?
Yes, NVCC.
Has a lot of potential for improvement by simplifying syntax, getting rid of the distinction.
So
level, not on the
Sure, it's difficult to do though. Yes.
Yeah.
Yes. Okay.
If it would be easy, you would have done it.
In 10 years, you would think so. Yeah. Yeah.
If transistors are abundant, then why only 16 gig of memory? Or more realistically, is there a chance to get at least, let's say, 200 key per thread in foreseeable future?
Is there a chance to get 200 gigs per thread in the foreseeable
200
future?
Kilos, 200 kilos per thread. You said it's 100 kilos per thread.
Yeah.
Is there a chance for this number to increase, or it will be the other way around? Number of cores increasing and memory still.
Okay, so is that ratio likely to increase or decrease? I think that ratio is likely to stay about the same. And it does vary across the product lines. At the end of the day, like the number of threads and the amount of memory is dictated by the fact that the GPU has a very real day job. And it needs to be profitable at that day job. And so these numbers are picked, based on availability of the memories from various memory manufacturers and how much yield we expect to have, and then there's some performance that results out of that, and then there's a very complicated multivariable optimization that decides what the mix is. You can imagine that that ratio could swing by 2 to 4x up, probably not worse than 2x down. It's in that region. But I don't see a near point in time where it would be drastically different. Because this other day job that the GPU has likes this balance. Yes, sir? Could we ship NVCC with a standard library that has device everywhere? We could. It's a pretty monumental task, just in its own right. It also would affect customers who want to use a particular standard library. Like, you would have to like my standard library now. Right? You couldn't use another one. So it's a difficult choice. Yes, sir? Can I speak to the differences between SIMD and SIMT? Yeah. Well, that could be another talk. That could be another talk. So the main difference is this D versus T distinction. Do you imagine that the operation is just mutating several pieces of data owned by the same thread? Or are you executing multiple threads as part of this? Now, the history of how GPUs came to this is long and interesting. But it basically goes back to the 80s, to work that Pixar was doing. Pixar developed this shading language called RenderMan. And in RenderMan, you wrote in a C-like language the math that each color channel would apply. And then your program would effectively get run 4 threads wide. Because you were writing in the C-like language, you were writing the scalar chain of evaluation for 1 color channel. And then Pixar wanted to run this in gangs. And that sort of set the tone for what later became pixel shaders. And then GPUs needed to run that. They needed to run this execution model. And so our view has never been that you're talking about multiple pieces of data in 1 thread. Our view has always been that you're running multiple threads, and then you want that vector efficiency. So you add a little bit more hardware. There's no question that SIMT takes some extra hardware consideration that you would not have when your view is SIMD. And so that may seem to some group of people as an undue tax. Like, there's definitely people who want the absolute barest, simplest silicon. But in our view, and I would say in the view of the Pixar engineers who designed RenderMan, whether they really formed this thought back then or but I'm going to ascribe it to them anyway. They saw that there's actually a balance between what is an elegant programming model that programmers will understand easily and will feel comfortable, and that hardware minimum cost. And this slight extra tax on the hardware, which, to be quite honest, you know, it's like 1% or something. That extra tax on the hardware is well worth it when you consider how much better you've made programmers' lives. And so, in general, you know, people are afraid of were in the past afraid of porting to the GPU because it looked like it was a lot of work. But most of the feedback we've received is that once you get over that initial fear, you realize that it's actually quite easier to get higher performance using that programming abstraction relative to you know, underbar, built-in in your code, top to bottom. You know. Okay. Another question. Speak up.
So you said that with Volta plus HMM plus NVLink, memory truly tastes like memory.
Yes.
Okay, and then you made an argument about TLS and this very skewed ratio of
Yes.
100K per thread. So does that mean memory doesn't truly taste like memory, or there's...
Right. So all right. So the question is, if Linux and HMM and NVLink and Volta, all of that together makes memory taste like memory, how do we reconcile that with the TLS question? You can look at it as an issue between, there are four storage durations in C++. There's static, dynamic, thread, and automatic. And static and dynamic storage durations are fully addressed by Linux, HMM, Volta, and NVIDIA. The thread and automatic storage durations have some other issues. So at the moment, we don't allocate any thread storage duration. We really don't know what to do, so we don't allocate it. And if you try to access thread local from a GPU thread, it would just block. Certainly, my preference is to find a way to explain this to you in an acceptable way in clause 4.7 maybe. And then for automatics, they work really great on the GPU, actually, right up until the time where you try to share a pointer with one of your buddies. But you can take pointers, and the pointers do work, and you can pass by a reference in a thread of execution. There's no problem with that. You just can't pass it with someone else. And okay, so your question is memory not really tasting like memory? I guess I'm going to narrow the claim to static and dynamic storage durations really do taste like memory. Okay, you were slightly first.
Yeah, I have one question here. When you talk about 100K thread,
Yeah.
we've got a single code block, which all the threads share. Then we've got multiple data areas for each thread. The 100K refers to exactly what? The amount of data memory per thread? What about the size of the thread? Take any of that? Or is that a totally separate block?
So the ratio that I showed is really just how much memory is on the board and how many threads are on the board, ratio of that. If your threads really only needed 20 kilobytes each, then everything else is just basically shared state, right?
Well, let me ask one thing differently. How much memory, how big a program can you stick, even though you've got 100K, which I think that means 100K data memory.
Yes, it's 100K data memory per thread. Yeah, the program can be arbitrarily large. It can be arbitrarily large and run arbitrarily long and run arbitrary control flow. Like there's no, some people have a notion, oh, GPUs can't do recursion, or they can't do functions, or they can't do function pointers. Like that hasn't been true for NVIDIA for like 10 years. So you can have an arbitrarily large program that's arbitrarily gnarly. It's just the amount of per thread state.
Maybe I got it wrong. Does the thread, does the program instruction memory reside on the NVIDIA chip, or is that reside in the normal CPU RAM?
The program memory will live in one of the two, but it doesn't. No. It's because it's migratable. Like it could start in one and move to the other a few microseconds into the job. You could canonically think of it as being in the GPU memory, but it's relatively small compared to that 16 gigabyte. I'm not sure how many people have gigabyte object files. I know actually NVIDIA has some, but But they're pretty rare. They're pretty rare. Okay, all right. That's it. So I'll take your questions offline at this point. I'll stick around. Okay.